Greedy. The simplest strategy there is, at every step, grab whatever looks best right now and never look back. Sometimes that's a disaster. But when it works, it's shorter and faster than anything else. The trick is knowing which is which. Let's see it, with no code, just pictures.
A greedy algorithm makes a sequence of choices. At each one, it takes the option that looks best in the moment, the biggest, the cheapest, the earliest, and commits to it. No going back, no trying alternatives. One pass straight through. That's what makes it so fast.
But here's the catch. Greedy is not always right. Make change for 6 using coins of 1, 3, and 4. Greedy grabs the biggest coin first, a 4, then needs 2 ones. 3 coins. But 3 plus 3 is just 2 coins. Grabbing the best local choice led to a worse answer. Greedy has to be earned, not assumed.
So when can you trust it? 2 conditions. The greedy choice property, the locally best choice is always part of some best overall answer. And optimal substructure, after you make that choice, what remains is a smaller version of the same problem. When both hold, greedy doesn't just work, it's provably optimal.
Signals that greedy might apply: you're asked for a maximum or minimum, the choices can be sorted by some obvious key, and taking the best one never blocks a better future. Scheduling, picking coins in a sane currency, and packing by value all fit. When in doubt, try to break it with a counterexample first.
First problem, activity selection. You have a pile of meetings, each with a start and end time, and one room. Overlapping meetings can't both happen. What's the largest number of meetings you can fit?
The greedy key is surprising. Sort by finish time, and always take the meeting that ends earliest among those that still fit. Ending early frees the room soonest, leaving the most space for everything after. Pick the earliest finisher, skip everything that overlaps it, then repeat. That simple rule provably packs in the maximum.
Next, the jump game. You're standing on the first cell of a row. Each number says how far you're allowed to jump forward from that cell. Can you reach the very last cell?
No need to try every jump. Just sweep left to right, tracking the farthest cell you could possibly reach so far. At each cell you can stand on, update that reach. If your reach ever falls short of where you're standing, you're stuck. If it stretches to the last cell, you made it. One greedy pass, one running maximum.
The boss. The fractional knapsack. You have a bag that holds a fixed weight, and items each with a value and a weight. Here's the twist: you may take fractions of an item. Fill the bag for the maximum total value.
Rank the items by value per kilogram, the bang for the buck. Greedily pour in the densest item first, then the next and the next. When the last item won't fully fit, take just the fraction that does. Because you can split items, always preferring the densest is provably optimal. The bag leaves full of the best value possible.
That's greedy. Take the best local choice, commit, and move on, but only when you can prove the local best leads to the global best. Activity selection, the jump game, the fractional knapsack, each fell to a single sorted pass. Simple, fast, and when it applies, unbeatable.
That's pattern 12 of 18. Next, intervals, merging, inserting, and scheduling ranges that overlap. Learn every pattern, plus hundreds more lessons. Master code. Master your future.
CodeSamur-ai